Last time I demonstrated how we can break our previous logic, kind of, by instead of passing around actual values, passing around the memory addresses where those values are stored. Because now we can do weird things, or things that previously would have been weird, like manipulating a variable in one stack frame from a method we call somewhere else, which has its own stack frame, its own table. And the biggest change, or the biggest new information, was the concept of a reference type. A custom data type, a structure like before, that is not stored on the stack alongside our other variables, but in a completely different part of the memory, which is way larger, but completely unorganized, called the heap. And you've also seen how by storing the structure on the heap and referencing it using addresses, we get different effects compared to what we've done so far with structures, or structs specifically. And today we're gonna have a little bit of a closer look at that, at some of the differences, and some weird side effects you can get, and some really cool things you can do once you have the ability to make indirect references to data, as in reference types. Now to start off, we're gonna try and get a picture going. Please, there we go. And then we're gonna write a little program. Let's see, we're gonna start here. And down here, let's make two very simple structures. Let's make one struct. We're gonna call it val. And val is gonna contain a single integer. Int I. Good enough. And we're gonna have the constructor, of course. Val. Yeah, why not? Int I. I equals I. This and this. No, I can do better. I can do better. Well, no. Arguably better. So we have a structure now, which contains a single integer value. Not exactly useful, but small enough that you get the idea of what it's doing. It's not going to take up a lot of space on my notes here, and more than good enough to demonstrate what we're going to try next. First, we're going to create a new value. Let's call it v, and we're going to use the new keyword, which for a struct doesn't mean too much. It's just formality at this point. And we're gonna pass some variables to the constructor method. Let's put in a 5, like that. And with that we have our variable v, which contains a single custom data type val, which is our custom arrangement of a single integer. Let's make a little table on the side again. Have to be careful not to get too wide in here. We had type, name, value, and whoop. Let's at least try to be a bit decent. And I don't like that music. Let's skip ahead. Sounds a bit calmer. Alright. With this, we would get a new val named v. And internally, again, this is a struct. This is a custom data type. We have a unique little table. Let's maybe make this a bit bigger. or wider at least. Type name value. And this is type int I and a 5. Right. So once we've executed this line, this is the end state. This is what we have in memory. This is our stack. There's one stack frame only active right now, because we're only in our initial methods here. And the value we store in memory is itself composed of potentially different other values. Right now it's just the integer. And that is our custom struct, which we store using the name v, which itself is just the address in our memory where we put it. We use the v in here for us programmers, but the computer doesn't care about the name, it only cares about the address it actually is. So when we use that in code, int b equals, just a reminder to get the value from a custom data type, from a struct in this case, we use the dot operator, so v dot I would reference v, so this value in here, and then with the dot we say go into the table that we found, and there go to I. We do that, and with that we get the 5, and we add 1, and that way we would get our next entry int b, which would then be 6, 5 plus 1. I lost my train of thought. Where was I? This is our stack frame, this is our structure. Right. These are just names. When I use the v in my program count here, of course I use our mental model and I just look that up in our table. There's a v, so this is the value we look at, this smaller table inside. But the computer just sees, look at address 1, for example. So address 1, the first entry in our table, that's where we need to look. And this table itself occupies only one space in memory. So this is one memory cell only, because it's only one value. And this would be one memory cell. If I add a second integer, for example, I might have 2 memory cells occupying the v, and for the integer after we would have only 1 memory cell, so 2 for that, 1 for that. The addresses shift around. That's a bit too complicated for us to keep in mind, so we only use the names. Simplifies things, but the computer knows it's all just addresses in memory. All on the stack. In this stack frame specifically, in this table we've created. And the comparison, if we do the same thing with a class, this code would still work, but in that case, our v would not be a subtable, and instead be just the address to somewhere on the heap. Let's say, let's just cut this off. That's the stack. And down here we have the... Doesn't look good. Let's nah. Let's keep that. Heap. Not as structured, and somewhere we just put down a table. Let me put that sideways, just to make clear it's not very structured. Type name value. And that was int I5. And this would just be somewhere on the heap, and that's the address. So let's say this is at address 9442, then this would be 9442. So in this constellation, if I reference v down here, I'm still referencing just an address pointing to our stack frame up here. So v still points to address 1 like before, but now in here it's not a table, it's just a redirect. It's another address. So if we want something like the dot operator from this value, the computer knows, okay, I have to first redirect to that address on the heap down here and then perform whatever action I wanted, like the dot operator referencing I, which is down here now. So we still go to the table first, but then we redirect to the heap. It's one extra step. Whenever we look up the value, it's one extra step we have to do. Well, not when we look up the value, because this in of itself is a value. It's an address pointing to the actual value we are interested in, but this address itself is also stored in memory. It's technically a value in memory, so I can use that as just a number and say, let's use w is equal v. In this constellation, what do I have with constellation today? We have another value, another val, w this time, and we copy whatever value we have in the table when we assign this. We do not copy this table. We don't create a new entry on the heap to store this table. We only copy the value, which is still 9442. So now both w and v point to the same address on the heap, the same table. So when I go and, actually let's put this maybe down a bit further this time. When I change I for v, when I set it to 1, I first see the v.i, which means we look up v, which is up here, and then we apply the dot operator, which means we first have to do the redirect down to the heap here, and then we look up I. That's here. And then we assign the value. So now down here, we change this to 1. That means v stores now a 1, effectively. But directly it stores only the reference to the table on the heap. And so does w. So when I look up w, well, w also points down to the heap, to the same table, to the same memory address. So w now also would give us 1. Both v and w are separate variables which have their own entries on the stack. They both occupy one distinct memory cell here, but the data we effectively use when we work with v and w is on the heap. Changing one changes the other. And this is especially important when you start incorporating some methods. Let's do that. We're gonna make it a void method. Actually, no, let's not make it a void method. Let's make it an int method. Int method, ingret, which will receive a val. Let's also call it just v. And it will then internally set v.I to v.I plus 1, which we can shorten, of course, to plus equals 1. That still works with the dot operator, so it's not important if it's a variable directly or something we referenced through the dot operation. It's still something we can do, the simplified, the shortened version. And because it's just a plus 1, we can also shorten it to plus plus. Oh, that looks like an I. Let's do that again. It's a semicolon. That's better. So we can do this. It will increment I, and then it will return v.I. So it will increment the value and then return it. Calling ingret, and actually let's do that for this. B is ingret v. Okay, increment and return. Ingret. Incredible. As before, we will still, let's cut this last line out, still get a new variable b. If we just follow the standard code, we still have a new value with a value 5. Let's change that down here again, back to 5. Create a new v, which points to an address on the heap, which internally stores just one integer in the table with a value of 5. That's what this first instruction does. This next instruction will call the method ingret with v. When we call this method, we get on a new stack frame, get a new table name value, and we start by declaring all the parameters, which is just one, just a val v, of course initially undefined, and then we take the value that was passed in here and put that in the table. And in this case, the value is actually the value from our table, so 9442, the address. And with that, we have already declared and initialized all the parameters. We can now start processing the code. And when we increment the I for v, we increment the I, the value, for this entry on the heap, 9442. So this is now 6. And when we return the value, we return this incremented value 6. We leave the stack frame, we go back to our original, method call is done, and we assign the return value, the 6, to the new variable b. So that's why this is the end state after those two instructions. What is important here is we didn't just get back the value 6, we also have it stored in v. If I look at just the code here, I would have the impression that v is filled with a 5. That's the value passed on here, and we didn't change v in any case. Like, there are only two instructions. One created it with a 5 and the other just passed it to a method. Nothing else is done. We didn't change v up here. But because it's a reference, because we pass on just the address where the data can be found, this other method can manipulate the exact same data we see up here. Because this created object, this v up here, is pointing to the same memory as this method, and when one of them changes this data, the other will also see that changed data. Change one, change both. So when we call this method, it means we are changing v. And we have to be aware of that. This is a side effect. As in, this is actually a term, side effect. And when you program, you have to be aware of this potentially happening. And there are different strategies around that. For example, we might want this to happen. I earlier was thinking about making this a void method. If I don't return anything and just have it increment I of whatever value I pass on, or I can just call this method, has v to it, and it will take care of the increment operation. It will increment the value on that object and not return the value we just incremented, it just returns, it's done. We still have changed v, and this might be intentional. We offshore the logic into a separate method, its own little island with its own little stack frame. Not our deal, not our business. It's happening on someone else's turf, but it's happening. We're still talking about the same value. If I were to change this back to struct, well, then we don't store an address in here, we store the actual value. Type name value, int I, that was initially a 5. Actually, this doesn't exist anymore. Right? I create a new value internally with a 5. Well, then I have this, it's in a struct now. So we store the actual table, the actual data. And when I call incred, well, I do get to a new stack frame. And I create the new table, type name value. And this is a val, this is also called v. We initialize or declare the variable, we initialize it with whatever value we passed on here. So whatever value we put in here is this little table, so we copy the entire table, type name value. And I5. And then we increment the I by 1. Still works just the same. It's just this table is now on our stack frame, not on the heap anymore. Not here. So we increment only this part. And value is now a 6. Alright. And with that we end our method. We don't return anything this time. Just we end this method. The stack frame is cleared. And we go back up to our original table. And v still is using a 5. Because we changed the memory address in this other stack frame. When we called this method with this custom type, we copied the entire data that made up this custom type. The actual value, the actual data we stored is copied because it's a struct. It's a value type. We store the value directly. So when we copy whatever's in the table, we copy the actual value. But with a class, we copy the reference, the address, which is what we store in this table. And therefore, both this method and our original code here talk about the same data. Back at the 9442, which is copied down here. And we get the side effect again. It took me quite a while to explain this part, but it's very important. I still sometimes run into an issue where I forget about that when I mix classes and structs in the same code. And for some reason I get a weird bug that some data either changes or does not change, counter to what I expected. And it's because I forgot that I'm passing on either the value when I expect it to change, or forget that I'm passing a reference when I expect it to not change. It's easy if it's with a keyword ref, which we talked about last time, because in that case we specifically note it down as we want to pass on an address. We want this other method to have access to the same data, the same memory address as our normal code. You have to specifically write that out with the ref keyword. So there's no accidentally passing on a reference and then wondering, why did my data change? With a class, with a reference type, that's not so trivial anymore. But again, it's also kind of useful because I can just pass on whatever object I have. This is an object. And this other method will be able to manipulate it without having access to the rest of my code. Doesn't matter, I just pass on the address on the heap and it will do its job on that part of the heap. Doesn't care what this object really means, where it's coming from, what it's doing, what I'm using it for. It's just somewhere on the heap. This method will increment the value. Done. And when you look at this, it's important that you don't mix that up with, I'm just gonna quickly remove the constructor here to get some space. Let's pretend the constructor is still there. Actually, let's keep that in there, just make it shorter. Val int I. We can move everything in one line, there's no issue there. I equals I. So constructor is done. And then the method. Let's also make this a void method, not void, void. Let's also call this ink red. But this one doesn't get any parameters. And so internally it will just do this, I++, and be done with it. So it's essentially the same code. It's just this time it's an internal method. If you remember that from 2 or 3? 2, I think. 3? 3 or more lessons ago. Instead of calling this method incred up here and passing on a value, I can just call it on v directly using the dot operator. Incred. This one doesn't get any values because it's the internal method here. And if this was the struct version, let's start with that maybe. We can keep this method around, doesn't hurt anyone. If it's still the struct, then we have our table, type name value, int I5, let's put like that. And calling this method just means we start with a new entry on the stack frame. We call a new method after all, but we are kind of starting with an existing table. So it's not just we start by creating a table that we fill with the parameters like we would do here. Because it's an internal method, we can assume that those variables we have already declared in the structure exist. They're not getting created, they already exist. This method simply works in the context of this existing table. So within this table. So while we should write this out as one table, technically on the new stack frame, That's only for our mental model. Really, we start with an empty table for this method, and this data is given. So we're working with this specific data already. And we manipulate the I in that table. Change this to 6. If you think about it in a different way, this was not just a method we call on this struct, struct value. It is a method we call using a reference, kind of. If you imagine this method being called anywhere, but being given a reference to the original data. If that makes sense. So we have this part of memory that holds the actual value for our structure, and our method can use that data, even though it's on an entirely different stack frame. It's a new method after all. It's a method call. We have a new stack frame. We have an empty table because there are no parameters here, but still it's a bit like we had ref keyword on this I up here. So we do have, in a way, those integer values, just like with the ref keyword. Initially 5, and then 6. Because we call it internally. It didn't matter that this is a struct. We're still talking about the same point in memory. Of course, this doesn't change when we turn this into a class. It's only that the table isn't stored here, but down here. But it's still, we take this data for granted as it exists already. We can use this data. It's kind of in here in our table, even though we don't have direct reference to it in the parameters and we don't declare it inside, it's already a given. They exist. Just like with the ref keyword. And being class or struct doesn't matter. Reference type, value type. In both cases, these methods operate with the actual data. This method here, that's outside of our class or struct definition, it doesn't have that luxury. It doesn't get to assume an existing table. It's not tied to any existing table. It will get a reference to the table if it's a class, or it will get a full copy of that table, this one down here, if it's a struct. This method has no idea what these tables are. Well, at least it's not tied to one. It will get a reference to one of those tables or a table as a whole. This method is defined inside this class or struct, and it's therefore tied to a specific version, a specific instance of that class or struct, either on the stack somewhere directly or indirectly on the heap. Let's change things up a bit, because so far this is actually just recap mostly. Let's have some fun with these data structures. Let's forget about the methods. Let's just focus only on the values in here. If I create a new value, I'm using the keyword new as a formality in terms of structs, because for structs, we've already secured the memory necessary for it on the stack. and we use it as an operation, kind of, for a class where we actually have to reserve memory on the heap first. Let's clean this up a bit. Like that. So we always use the keyword new. And we followed up by the constructor call. Always. You can't get a value any other way. You have to call the constructor. You have to first use the new keyword and followed up by a specific constructor call. Thing is, there's a specific constructor that we can just assume, and that's the constructor without any parameters. And the reason we can assume that is because I didn't write any constructor down here. Val doesn't have any constructors, I erased that. If we don't define a constructor ourselves, the computer will just help us out and... What am I doing? We're not there yet. We'll just create an empty constructor. As in, a constructor that doesn't get any parameters and isn't doing anything. The default constructor. It will only do so if we didn't provide any other constructor. Once we've defined our own constructor, the computer will not add its own anymore. It's basically just a shorthand for I'm only having a simple class with a simple value, or maybe several simple values in here. There's no complicated initialization routine, there are no invalid states I'm trying to avoid, it's what it is. I still have to write that out when I call it though. You can assume the constructor exists, the default constructor, you can use that, but you have to still write that out. Now, yes, in more modern C#, you can forget about the val keyword. You're still calling the constructor, but you can simplify it to this. But I'm gonna write this out as full version. I want to make it more clear, and also because this simplification only works in specific circumstances, like if I'm initializing the full variable directly, for example. Let's not get into the exceptions for all the special syntax sugar we have, even though it's pretty cool. So this is now a valid statement. This is creating a new, this is a class, so a new space on the heap for one value, for one val, using the default constructor. So constructor that's not doing anything. So we only reserve the space. We have now space for exactly one integer and do nothing else. And this is valid. Why am I pointing that out? Well, it means we have now down here a table with an int I and what? I didn't have a constructor, so what's the value? So we might assume it's undefined. The same as if I just write down int I in here. If I just declare the variable, it's undefined, it doesn't exist. The computer will simply not allow me to use it until I provide a value. And while that is certainly an interesting thought, it's not how C# does it. Mostly because that would make a lot of things very complicated. This observation of I've already declared the variable, I've never assigned a value, is certainly useful when you write a simple piece of code. And it's doable enough in that scenario. But keeping track of that over a whole program is very difficult, because there are so many different ways that variable might get a value, and some of them are impossible for the compiler to notice. Especially once we talk about pointers, which we're not going to do, but I mentioned them last time, I think. They allow you to completely circumvent the compiler and work with memory addresses directly, and so, yeah. The special logic with undefined is only allowed for normal code, when I just declare a variable freshly in my code, locally within a table for my stack frame. It does not apply when I create a new instance of a custom data type. This has, in fact, after this construction is done, a very well-defined value. The runtime, the computer, will make sure that this has a defined value. Even if you do not decide what it is, the computer will decide for you. And the decision is, set all the bits in memory to 0. Keep in mind, we have only ones and zeros in memory, and it will start by setting everything to 0. What does it look like? Well, it depends on the type we're storing. This is now an integer. Literally an integer type. So having all bits set to 0 is just the number 0. So after we create this, our v stored on the heap will store a 0. We didn't need to provide one with a constructor. We didn't need to call the constructor and set the value to 0 first. This never happened. Even the compiler doesn't do this. It doesn't need to. This is what the compiler provides. Just basically a formality to ensure that it does have a constructor, even if it's not doing anything. The moment this memory is allocated, the first, well, not the first thing, but one of the earliest things that happen is that all the memory inside the allocated area is set to 0. All the bits inside the space we just reserve for ourselves are set to 0. And then we apply changes and set those bits to something more meaningful, maybe. With this code, we don't set it to anything else, it's gonna stay at 0. The same, by the way, would also happen if we do this as a struct. We do this as a struct and get the table in here. We'll also start with a default constructor, which is the same as with class, and it will have int I 0. We don't need to specify it. If it's in the stack, if it's on the heap, doesn't matter. It will start with setting the memory to 0. That leaves an interesting question now. If this, let's go back to class first. If this is not an integer type, but okay, let's make it interesting. Bool. This is not a number at all. What is a bool gonna be? Well, everything 0 means it's just 0. False. No. Off. So integer types, or numbers in general actually, all start with the value being set to 0. As in the number 0. And Boolean will start as false. So when I do this as a bool, it will start with zeros in memory, but as far as our program is concerned, that's of course not called a 0 anymore, but a false. And now I'm gonna really trip you up, because we're gonna introduce a different variable now. We're not gonna call it I. I'm gonna introduce another val. Yeah, no, let's call it n. What did I do here? We have a class val which stores itself. So this n internally also stores another val, which then stores another val, which stores another val. So what does this even work? What is going on here? What is happening here? Well, first of all, of course, it is valid. Otherwise, I wouldn't show this to you. You can do this. This is a reference type, and reference types can store references to themselves, or at least to instances of themselves. No, actually, they can also store references to themselves. If you think about it, it's a class, a reference type, so we have an address to somewhere on the heap. And we'll make this a bit larger now, type name value. We have the val and 9442. This is perfectly possible. Okay, this looks kind of ugly, but just like our v up here references heap address 9442, so can this table in here reference address 9442. That it itself is stored at 9442 doesn't matter. It's just referencing that address. Like my house number is visible at my house. My house itself tells someone who looks at it where it can be found. I have my own address plastered on the house at my address. That's not really all that surprising, is it? Of course, that is not all that useful. It is a lot more useful if we don't store our own address, but someone else's address. But before we get to store another address, we have to question if the memory, as we read this out now, is initialized with all zeros. Does that mean we are now referencing address 0 in memory? What is address 0 in memory? What does it do? What is at address 0 in memory? And the answer is nothing. Address 0 is actually a very special address in that it is not storing anything useful. You will never have anything actually stored at address 0. I mean, okay, yeah, to be fair, the computer will put stuff at what we would consider address 0, but we can't use it. Address 0, an address, a reference type where we fill everything with just zeros, has a special meaning. Actually, this should still be 9442. This down here should be all zeros. It means there is no address. That's all it means. Having an address, a reference to somewhere in memory where all the bits are set to 0 means this doesn't point to anything. There is nothing here. We don't have a reference. It is a different way of saying it's undefined. But it is a value we can store in this table. So having value set to a new address fills it with data. But I can also have an address filled with data in our table. But point to nothing. So just defining or just declaring the variable would just mean I have nothing in here, but I can actually initialize the value. I can provide it with the address for 0 to satisfy the compiler, and that I do now have an actual variable w I can use. There is a defined value in here. It's just that it's meaningless. It's pointing to nothing. I can't use w, but it is a valid variable now. Fully formed initialized variable that I cannot use. I mean, yeah, you can use it, but there is nothing stored in there. It's not pointing anywhere. And for that, we have actually a special keyword, because we don't work with addresses directly. I can't write the address myself. And the special keyword we use is confusing for a lot of people that speak. Well, I know it's confusing a lot of Germans when they learn it the first time. It's called null, which is written the exact same way as the German word for 0, null. So that's not confusing at all. I'm not sure how many other languages have the same issue, but this is the official keyword, null. And it just means that this is an address, a memory address, that's pointing to nothing. It is literally zeros, if you look at the actual data. So when we create a new val up here, well, this table internally is null. And so is this w. It's actually filled with data. I can access this value. It's just all zeros. It's null. It's meaningless. If I go for v dot n, well, I go to v. I see it's an address, so my dot operator needs to first redirect to that address down here. And then I can look at n and take the value from here. But if I go to w, well, if I try to go to w, I go to my table, I look up w, and then I try to resolve the dot operator. I see it's a value, so it's a reference type. I have to check that out. But when I try to redirect to the proper address on the heap, it's null, meaning there is no address to point to. There is no data I can reference. It is not much different from I'm looking up a value that's not defined. Yeah, come on, undo. Okay, let's do that by hand then. So w.n, applying the dot operator to w, which is right now null, is similar to just writing int a, and then saying int b a plus 1. Even if I have an a declared, I have no value defined for it. I can't look up a value for a because I was never provided with one. So this doesn't work. This is illegal. And in the same way, I can't do anything with w. It is itself fully formed. I can use this variable for some things, but I can't look up a value for it. The dot operator would require the data in w to actually reference something on the heap, to actually allow me to redirect somewhere. But it's pointing to nothing. I can't. This too is illegal. And actually a common source of errors. Maybe if you look up the keyword null and mistake, you will find some quite famous quotes. The thing is, it's in the end just a tool, and as much as it has caused issues in the past, the language has been updated several times to improve handling of null, to avoid issues like my earlier one where I tried to interact with nothing. And the current language has some quite nice features which we will get to eventually. But those are more like convenience features and they're not important for you to understand right now, so we'll move that out for later. So that is the meaning of null. It means when we create this new val for v and we initialize everything with zeros, we store a null. So we can do v.n, no problem. It's just n will be null. But we can then assign a new val to that n. v.n equals new val. And what that does is we reserve new space on the heap. We call the default constructor right now, since we never made one. This might be address 42. Let's keep it simple. Which also has a table, type name value, val, and null. And this table is now referencing address 42. So our address here points there, and this one then points here. We have our W, we have we have V, we have V.n, and we have N.n. V is in this table. It's a reference type, so we have to redirect to that address. Okay, let's go to this table then. We continue here with N, all right. N is in here, it's a reference type, so we have to redirect to that address on the heap. We go over here to this table, and then we look up N. N is in here, it's a reference type, so we have to look up, oh, it's a null. Okay, we can't. But we could assign a new val. So we reference a new space on the heap. It's gonna be 333, which has its own table, of course. Val n, which initializes with all zeros, so it's null. And we assign that to that n. And so we have now in here 3, which points there. And we can keep this up for as long as we want. v.n.n.n.n.n.n.n.n.n.n.n without end. If you have a look at this little sketch here, we start with this one value, and connected to that is this table, and connected to that is this other table, and connected to that is this fourth table, if you count this one up top as well. Let's say I would store not just one value, but also the integer I, like before. Well, then this thing would have an integer I in here, and this one would have an I in here, and this one would have an I in here. They all would store one integer, distinct integers, all on their own. And now consider that instead of doing this, I can do something like v equals v dot n. Now think about a moment for what this is doing. On the left, we have just the variable v. No dot operator, just v directly. So we want to assign something to v. We want to change this entry, this single value in the heap. On the stack. Sorry, on the stack. And what we assign is v.n. The dot operator is precedence over the assignment. So first we have to go to v. Alright, it's here. It's a value type. So the dot operator has to redirect to that address down here. We're in this table now. We look up n in this table and get 42, an address. And that is the value we copy and assign to this v up here. So we change this to 42. Which means, of course, we don't point down there anymore. We are now pointing straight to that. We completely forgot about the address for this. This address is gone. We don't know it anymore. And we don't have a way to find it anymore either. This data on the heap is now completely lost. We have no way to find it anymore. And this would actually be an issue. This is one of the big issues you have with managed memory, which is what we are doing. If we were to work with pointers, well, then we would be screwed. If the memory was entirely managed by us as the programmers, well, then this would be called a memory leak. We have now permanently occupied space in memory that we don't access anymore. Now, to be fair, that's not actually true, because we could occupy that memory again technically and just override it, but this can cause other issues. Point is, it's a problem. This kind of thing happens all the time, and it's a problem. So how do we deal with that if it's happening all the time? If the system is working like C#, which a lot of languages work the same way, we have this thing called the garbage collector, which is a background process. So whenever your program is running, your simple just three instruction program, the garbage collection is active in the background. And what the garbage collection is doing, it's constantly checking for these orphaned little pieces of memory that we lost. We can never get back again. This data is lost to us forever as the programmers, because we don't know the address anymore. And since we lost it anyway, the garbage collection comes along and says, good, since you have no way of using this data anymore, it's completely fine for me to just erase it to make space for new data later on. We don't even notice it happening. We can just completely drop that memory address. We can completely forget about a large chunk of the heap. Doesn't matter how much, how many different pieces, how large those pieces are. We can completely forget about it. We don't need to worry about it. We can forget the address, and we don't get the data back, but we do get the space they occupied back. It can just take a while. That's the problem with garbage collection. It is actually active work, figuring out which parts of the memory are still in use and which are not. Because maybe we do have somewhere the address still tucked away, ready to be used, either up here in the stack or maybe down here in one of the other parts of the heap. Garbage collection itself is actually a very, very complicated topic, if you want to get it to a decent performance at least. But it's very well optimized, it's very known problem, And people smarter than any of us. Okay, I would have said this a couple of years ago. By now, I'm not so sure since Microsoft is involved, but still, there are still a lot of very smart people working on stuff like this. They know how to get the garbage collection very optimized and very fast, so you don't really have to think about it. There might be cases in the future when you write large programs where the garbage collection becomes important performance-wise. Either because you need so much memory all the time that you have to wait for garbage collection to free stuff up, and maybe you want to interact with it a bit to tell it, please start cleaning up stuff right now. I'm gonna wait for you. You have free reign. I need that memory. Other times, maybe you tell it to please slow down for a moment. I need the performance. Don't hog the CPU for yourself. But that's really more the advanced stuff, and it's rare because it is really well implemented. Anyway, that's just in terms of garbage collection. We give up the address. We don't have any access to that part of the heap anymore, so the garbage collection simply frees up that memory so it can be used again for something else. But something else we've done is we've moved up this chain. There was another piece of data in here that we looked at first, and then we looked at this thing. And in both cases, we looked at that piece of data through the same variable v. V is now looking at this table here with different data, different memory cells, with potentially different data at least. It was looking at this table that was on the left here before then. The same name, the same variable even on the stack, the same memory cell is used to target two different other parts of the memory. Now imagine I do not completely drop the address. What if I say I have val let's call it I, just to be confusing. I'm gonna start at v. I is gonna be first start looking at 42 as well, right now. And then we're gonna check if I dot n. So if the value I is storing for n is not null. This is a comparison we can make. The not equals can be used for booleans, though maybe they're not that useful there anymore, but you usually use them for numbers. It can also be used for addresses. If whatever address I internally stores for another value is not null, then we simply change I to I.n. So we point to the next one. So we start at 42 and we point to this table down here. And if the n in this table is not pointing to nothing, if it's not null in here, we're gonna change our value up here to point to the same address. So we're gonna change this to 333 to this one. And then we could check again if I dot n not equals null, I equals I dot n. If this is not pointing to null, well, let I point to the same thing that this table down here is pointing to. Of course, in our example, this is null. So this condition is no longer true and we do not assign I to the next one. You see that this code here is identical to this code here. And instead of repeating the code manually, we can of course have it repeated by the computer. Turn this into a loop. So if we up here had another v.n.n equals new val, gonna write it to the table right now, and we had another pointing up here, well, this thing would start at this table, or point first to this table, and because this has another table it points to, we would iterate once through the loop, and now I would point to this table, and then we would iterate once more and point to this table, and then we would stop. And maybe something in the recesses of your mind suddenly signals you, hey, I have seen this before. At least I'm hoping you do, because there's something familiar about this. You can see it again. This, followed by this, followed by this. We start up here before we enter the loop. We initialize our I here. Then we make a condition, see if we want to repeat or not, if we want to enter the loop. And then inside the loop, what we do is we change our I to the next value in order. Hopefully this reminds you of a very specific loop we discussed, which is appropriate for cases like this as well. It's the for loop. So I'm just gonna start wider on the left right now. For val I equals v. Make a semicolon to separate the first part of the for loop, followed by the next one, the condition. I dot n not equals null. Another semicolon to start the third segment. No, wrong direction, that's the semicolon. I equals I dot n. We have now created a sequence of 3 different tables on the heap, starting with v and then manually just adding another one and another one. And then we created a for loop that can jump through all these 3 tables. And every single time we could, if we wanted to, use I to look at an integer value. And every time we would look at the different integer value. Now let's say I have an int c. We start at, let's say, 0. Right? I'm cramming a bit, I know. And then in here we would increment c by 1. Well, then we could make a condition if c equals 1. Let's move this down a bit. and move this over to the left again. If c equals 1, then x say 0, then no, let's change this. Then let's do x equals I dot I. That's a semicolon. I'm getting confused. That's better. Alright, I'm cramming a bit, but imagine what's happening here. This for loop will first look at this table, then try to go to this table, and then try to go to this table. And each iteration of this loop, I, the variable I, will point to one of these 3 tables. It will go through all of them in sequence. And while we do so, we will constantly increment this variable c. When we look at this table here, this part of the heap, it will be 0. When we look at this one, it will be 1. We look at this one, it will be 2. And this condition here will check for a specific value. Right now it's 1. And if it's a value of 1, it will copy the value that's stored in I in that variable into the variable x. As in, it will store the value that's stored in the I of I. That will be stored in x. So c is 0 in here, 1 in here, 2 in here. So we will only copy the value I dot I into x when we are looking at this table. We could alternatively say, if we're looking at, maybe make a different value, 10, I'm gonna set I dot I to x. We start here, don't do anything, then go to here, set I to 10, and then go to this one, and that's where we end. We went through all 3 memory parts with one loop and changed one specific table in here, only one, very specific one. And we can just change the number in here to target a different one. So a simple integer number here determines where in memory we change the value. It might not be an address, memory address, but we can use it in place of an address to target a specific table in here. And what's even more interesting is that we only have 3 tables, 3 different instances of the class val in here, but there's no upper limit. This can point to another one, and this can point to another one, and this can point to another one. There can be as many as we want. We can have as many different values stored in here as we want. We can just continuously add more. We can add more in a loop. We can, for example, inside the loop, instead of just setting, for this scenario, this I to x, we can also say, actually, let's drop this loop altogether. Let's make a different kind of loop. Now let's start with an. Let's start still with an val. With a val I equals v, like before. But then we make a for loop, but this one is an integer-based one. Int c equals 0. C less than 10. C++. Very standard for loop this time, with just an integer. And every time we say I can also drop this actually. I dot n equals new val, and do so inside the loop. And then I equals I dot n. We point I to that newly created val. For exactly 10 iterations, that's fixed by now. We fixed it at least to 10 with this code up here. We will create new objects and attach them to the existing V at the end of this chain. And then we let I point to that new last chain and add another value. Let I point to that, then create another value. Let I point to that. We do that 10 times. And if I change this to 100, we do that 100 times. And the for loop I showed earlier is able to step through this entire chain and target a very specific element within that chain. And if you're not quite sure what good this would do, think about it this way. We don't need to create 100 different entries in this table. We don't need to come up with 100 different variables that we need to declare in here to store 100 different values. We only have this one actual initial value v and just another entry I as a temporary holding area for a temporary value that is constantly changing. V is still the initial first object we made, our entry point, so to speak, into the chain where it starts. And I could be any element in the chain. We can add new elements. We can step through and find a specific element. And each of these elements can store an integer. We can use integers to control how many integers we use, and we can access all those individual integers in each of these elements and do something with it and change it. We are no longer limited to the number of names we can come up with. We don't have to manually declare every single memory cell we want to use. We just use them. And to access them, we use just an integer to count how many times we've stepped through here. Like a pseudo address, but one that we directly control. The compiler has no issue with that. It's not a pointer. We're not storing addresses in memory directly. We're just abusing this indirect method of referencing a reference to a reference to a reference to a reference. In effect, we have now created a linked list. We have a list of numbers, of integers, that are linked together with references, with memory addresses that tell us where the next item can be found. And that next item will also contain a reference to the next item that can be found. And this opens up a lot of possibilities. This is just the simplest case. It's only possible because we're not storing data in our stack up here directly, we're storing the addresses. We're doing things indirectly. This one level of indirection, this one level of redirect is kickstarting a whole field important for computing. Especially in a language like C#, where we want to avoid working with memory addresses directly, but still want to have kind of the feature of unlimited memory we can access directly at our own terms. And with that, we're gonna end it for today. Next time, hopefully at... What just happened? I mean, it was good timing that it broke down now, but why did it break down at all? Oh well. Very good timing. Oi. So, yeah. That's a quick introduction to the weirdness of working with references and reference types. Keep in mind always, are you working with a value type, a struct, or a reference type, a class? And what does that mean for calling other functions? How do those functions, sorry, not functions, methods is what we call them in C#. What do those methods do? Are they contained within your custom data type? So are they automatically referencing a specific entry in the memory, specific table? Or is it a method outside of your custom data type that receives a copy of that data? Or is it a method outside of your type that receives a reference to that data? Beware of side effects. And the last bit was just to give you an idea of the great many possibilities that are now open to us because of references. Right then, see you next time. Bye bye.